Okay. Good evening, everyone. So let's get started. So we are in the final chapter, that is solution to partial differential equations. And in that, we are looking at how to classify different types of partial differential equations. And in this, we have seen, so it is important to classify PDEs because the application of initial conditions or in boundary conditions and also the solution methodology will apply to solve the PDEs depends on the type of the PDE. So that is the reason we wanted to classify the PDEs. And we said there are, again, several ways PDEs can be classified. One was based on the linearity, right? Whether it could be linear, non-linear, and so on, or quasi-linear. And then we also said based on the highest degree that is available. So that is basically based on the order of the PDE, right? It could be first order PDE, second order PDE, and so on. And the third one is we are looking at particularly a way in which classification of second order PDEs. Because we generally encounter second order PDEs, we said we want to classify them, the particular case of second order PDEs. So in that context, we considered a general equation, which was A, or general second order PDE, A times dou square phi by dou x square plus B times dou square phi by dou x dou y plus C times dou square phi by dou y square plus E times partial phi partial x plus F times partial v partial y plus g times p equals some, I think I missed a e here. Okay, so let's put this back into t. This is e, and this is f. F times phi equals some g. Okay, so that's what we said. Okay, so we said this is the general equation. Just 1 second. Okay, so we said this is the general equation which we wanted to solve. This is second order PDE, and then we said across where A to G could be functions of x, y, and phi. Again, we said if this is only a function of A and B, A to G are functions of x, y, then this is basically a linear PDE. And if they happen to be functions of phi, then it is a nonlinear PDE. And if the A to C are functions of x, y, whereas D, E, F are functions of phi, then we said that is basically a quasi-linear PDE, right? That's what we discussed. Now, in order to, we also said that there are some curves that are known as the characteristic curves, which basically patch the different solutions together. They patch different solutions together into one full solution. And these characteristic curves, along these characteristic curves, the second derivatives of this independent quantity could be indeterminate, right? As that's what we said. This is essentially the second derivatives of independent quantity phi could be indeterminate. Okay. Okay. So in that context, we considered what is the differential change in the partial phi partial x. I mean, this is the differential change of partial phi partial x between 2 points. Let's say xy and x plus dx and y plus dy. So we're considering xy as 1 point. The other point is x plus dx and y plus dy. Okay. Then we wrote essentially this differential change in phi x as partial phi x by partial x dx plus partial phi x by partial y dy. Okay, that means what does this mean? This is partial x of dou phi dou x. So this is actually second derivative of phi with respect to x. Okay, that is going to be dou square phi by dou x square dx plus this. The second one is going to be, there is already derivation with derivative with respect to x. Then you have y. So this is going to be dou square phi by dou x dou y or dou y dou x of dy. Right. This is equal to differential change in phi x. Right. That's what we obtained. Similarly, we can write partial phi y equals partial phi by y partial x dx plus partial phi y by partial y dy. That is going to be equal to, the first one is a mixed derivative, partial square phi by partial x partial y dx. The second one is the second derivative in y, partial square phi by partial y square dy. This is equal to, on the left hand side earlier, it is basically d phi y. Okay, so that's what we have obtained. So these are basically differential changes in the first derivatives. Okay, then essentially we said, okay, I want to recast this equation in a slightly different way, and that equation we have recast as, to be consistent with these equations, we wrote this as a times dou square phi by dou x square plus b times dou square phi by dou x dou y plus c times dou square phi by dou y square equals h, where h is nothing but everything that is sent to the right hand side except for the first three terms. That means all the last three terms to be sent to the right hand side. That is essentially g minus, you have d times partial phi by partial x, e times partial phi by partial y, plus f times phi. Okay, that's what we have. Now I have three equations. This is equation number 1, this is equation number 2, this is equation number 3. So in each of these equations, what you see is that there are terms which are partial square phi by partial x square. Okay, partial square partial x square, partial square phi by partial xy. Then you have partial square phi by partial y square. Similarly, you have second derivative of phi with respect to x, with respect to y, and the mixed derivative. So we can arrange these three equations in a matrix form where the unknown is the second derivative. Okay, that means we can write this as the matrix. Okay, so that is the matrix multiplied with dou square phi by dou x square, dou square phi by dou x dou y, dou square phi by dou y square. Okay, so that's what we have. And then from the first equation, we know that this is equal to dx times dou square phi by dou x square. So this is dou square phi by dou x square entry. So this is dx. And then we have for dou square phi by dou y square, we have coefficient is dy. So this is dy. And then there is no dou square phi by dou y square term here. So as a result, that is 0. Okay, so that means 0 times dou square phi by dou y square equals, on the right hand side, we have differential of phi x. Okay. Similarly, I have this mixed term with dx, second derivative with respect to y, dy. So there is no dou square phi by dou x square. We have dx dy equals d phi y. Okay. Similarly, for the last equation, for the third equation, we have a times dou square phi by dou x square, b times dou square phi by dou x dou y, c times dou square phi by dou y square equals, on the right hand side, we have h. Okay, so this is essentially the same equation in matrix form. Now, what we have is, now we want to, we have said that essentially across or along a characteristic line, across a characteristic line, the second derivatives could be indeterminate. Okay, so the second derivatives could be indeterminate. Okay, so that means what indeterminate form means? It is 0 by 0 form, right? So I can now calculate. Yeah.
Sir, is it like across or along or both, sir?
Yeah. So essentially, it is along a characteristic and across as well. Okay. So what we're trying to do is that along the characteristic, it is going to be indeterminate, and then when you cross it from this point to this point, what you end up doing is that you take the this differential changes dx dy tending to 0. So essentially, you are actually lying on the characteristic line. So it is, the definition is along the characteristic line, they are going to be indeterminate. But then the way we are trying to solve it is, we are trying to take 2 points on either side of the characteristic. Okay, let us say this is xy, and then you have x plus dx and y plus dy, and then you are essentially saying that this dx dy basically tend to 0. Okay, which basically gives you the concept of derivative, right? So when we say I'm calculating derivative across this thing, then we are actually trying to calculate derivative on this line, okay, which happens to be one point along the line. Now, now why is this important? This is important. That means that there is a jump in the solution. Okay, there is a jump in the solution when you go across a characteristic line, and the jump is what is leading to this indeterminacy of the second derivatives. Okay, so the definition is actually along the characteristic line, but then we are taking the second derivatives, we're evaluating them across the characteristic line with the dx dy tending to 0. Okay, so we're going to apply.
Thank you, sir.
Yeah, so we're going to apply. So now what we want to do is that we want to calculate the second derivative. Let us say I want to calculate dou square phi by dou x dou y. Okay, I want to calculate this quantity. So I'm going to apply the Cramer's rule only for this case for the very first time in this course. So how does Cramer's rule work? Essentially, you want to calculate this quantity. So this quantity means you're going to replace this particular column with the right hand side vector. Okay, so that is going to be your numerator divided by the denominator is the existing a. Okay, so that is how it's going to work. That means dou square phi by dou x dou y. If I want to calculate dou square phi by dou x dou y, if I want to calculate, I'm going to write this as modulus of the first column remains as it is. This is zx0a. And second column, I'm going to replace it with this column. This is going to be d phi x, d phi y, and then h. Third column is going to be same as before, 0, dy, and h. Okay, I think probably, sorry, 0, dy, and c. This you probably remember from your high school mathematics. Okay, and then denominator, the a remains as it is. So that is going to be dx, dy, 0, 0 dx dy, and then we have a, b, c. Okay, so that's what we have. Now we want to equate this to 0 by 0 form, because this is going to be, the second derivative is going to be indeterminate, So essentially, then let me first, if this is the case, let me first equate the denominator equal to 0. So let us say the denominator equating, denominator equal to 0. What we have is dx. So I take the determinant of this quantity. That's going to be dx times c times dx minus b times dy minus dy times minus a times dy plus 0 equals 0. Okay, that is what I obtained. Then if I'm going to divide with let us say d x overall, I'm going to get a times dy by dx. So if I divide with dx square, okay, dividing with dx square throughout, so I'm going to get a times dy by dx, and then I'm going to get minus b times dy by dx, and then we get plus c times dx square by dx square. So that is equal to 0. So we obtained an equation, a quadratic equation, and the quadratic equation is in terms of dy by dx. Okay, that means if I solve this quadratic equation, I'm going to obtain the slope of a particular line. Okay, so I'm going to obtain the slope, and that slope we know that from from algebra, we know that dy dx equals minus b plus or minus square root of b square minus 4ac by 2a. Okay, all right, so that means this is going to be the slope of the characteristic lines. Okay, so this is going to be the slope of the characteristic lines, and then we also know from algebra, from calculus, we know that essentially if b square minus 4ac is can, depending on the value of this discriminant, right, that is b square minus 4ac, we can have the number of roots will differ. For example, if b square minus 4ac is less than 0, then we have if it is less than 0, then there are no real slope or no real characteristics, right? Because this is going to be imaginary number. Similarly, if b square minus 4ac is equal to 0, then we have one real characteristic, and the slope of which is given by this expression. That means you can have characteristics, but then both the characteristics will have the same slope. That means they are going to be falling one on top of the other. Okay. Similarly, if you have b square minus 4ac is greater than 0, then you have two real characteristics. Okay. That means you have only imaginary characteristics in the case of b square minus 4ac becoming less than 0. Okay. So that is basically giving you what are the slopes of these things. Similarly, now if we equate the numerator equal to 0, that is dx0, if this quantity, so let's, okay, so if we equate the numerator equal to 0, okay, so that's what we have. That means I'm going to write this as, this is going to be dx times c times d phi y minus h times dy minus d phi x times minus a dy plus 0 equal to 0. Okay, that's what I have. So this is basically going to give me, if I divide with again with, let us say, dy everywhere, so I'm going to get a times d phi dx, and then plus c times dx by dy times d phi y minus h times dx equal to 0. Okay, so if we solve for this equation, this is going to give us what is the value of phi x, phi y, okay, in the xy plane, okay, or we are going to basically get what is phi x, phi y from this equation, okay. So which is basically going to tell you that these are the characteristics, okay, of a particular equation, but which we are not really concerned at the moment. We are interested in knowing how many, what are the slopes of the characteristics that a particular given equation has, okay. So we are only, but then of course you can always find the characteristics also, which is useful in certain cases, which I will touch upon a little later, okay. So then, so that means if you have b square minus 4ac less than 0, you have no real characteristics. If b square minus 4ac is equal to 0, then you have one real characteristic, and if it is greater than 0, you have two real characteristics. Now, this behavior is attributed to some names, and these names are basically, if this discriminant is less than 0, then we call such an equation to be of elliptic type, not Euler, to be of elliptic type, and then if it is equal to 0, we call it as parabolic type, and if it is greater than 0, we call it as hyperbolic type. Okay, so these names are have been derived, or because of the similarity of this discriminant to the conic sections that you probably might have learned, right? So in conic sections also you get a similar discriminant, and depending on how you cut a cone, right, you're going to end up with an ellipse, or with a parabola, or with a hyperbola, and so on, right? So it's basically coming from the conic sections names. That is the only similarity that it is there for these names to the PDEs. Okay, other than that, there is no other resemblance. So only resemblance is to the conic sections. Okay, now now we are able to classify them. Classify a general PDE based on its coefficient. Now, what we see is that while classifying, you see that we are only making use of A, B, C only. We are actually not making use of H at all, right? H is not used in the classification. That means we are actually making use of the coefficients of the leading order derivatives, right? So the classification of second order PDE, so the classification of second order PDE depends on coefficients of highest derivatives, okay, in the equation, not the other one. So we are only looking at the coefficients of phi xx, phi xy, and phi yy. That's all. Okay, so that is what we are looking at. Fine. So now let us look at what does this mean. So if you have, if the b square minus 4ac is less than 0, we said this is basically an elliptic partial differential equation. Okay, now that means a PDE is of type elliptic if b square minus 4ac is less than 0 in the entire region, okay, in the entire domain or region in which the PDE is being solved, okay. Only then we call it as an elliptic PDE, and it has no real characteristics, okay. And a few examples of elliptic PDEs. Elliptic PDEs are, the first one is the Laplace equation. Okay, in 2 dimensions, if I were to write it as dou square phi by dou x square plus dou square phi by dou y square equal to 0. So here you can see that your A equals 1, C equals 1, and B equals 0. Okay, so if I calculate b square minus 4ac, this is less than 0. Okay. Similarly, you have the other equation is the Poisson's equation, which is dou square phi by dou x square plus dou square phi by dou y square equals something on the right hand side, some forcing function f of xy. For this also, you'll see that b square minus 4ac will come out to be less than 0. Another third example is the Helmholtz equation, okay, which is del square phi plus alpha square phi equals some 0, okay, or it can be something on the right hand side, where delta here or del square refers to dou square phi by dou square by dou x square plus dou square by dou x square. Okay, so delta is the nabla operator. Okay, fine. So these are a few examples of elliptic partial differential equations. Elliptic PDEs are usually solved in a closed domain or region. Okay, so that means if you have a closed domain or a region, which we can call it as omega R, so that is in which inside which is what you can solve an elliptic PDE. Okay, and we need to specify boundary conditions on the boundary of the domain. Okay, so for example, either the value of the dependent variable, that is phi, could be specified on the boundary, okay, or the normal derivative of phi could be specified on the domain. That means partial phi partial n, where n is the local normal direction, okay, or a combination of these two can be specified. That means you could specify some a times phi plus b times partial phi by partial n equals some c3. Okay, this is basically specifying combination of phi and partial phi by partial n. For example, specification of, or to be descriptive, so specification of phi, the dependent variable itself on the boundary, is called as a Dirichlet boundary condition. specification of the gradient of the dependent variable is called von Neumann boundary condition. Okay, and specifying a combination of these two is known as specification of a mixed boundary condition. It's called mixed boundary condition. Okay, so it can be any of these can be specified on the boundary. Now, once when the boundary condition is specified on the entire only when boundary condition is specified on the entire domain, entire R, we call that problem as well posed for elliptic problems. Okay, only then we'll be able to solve an elliptic PDE. Okay, now you kind of so what I mean to say is that the boundary condition need not be the same on the entire domain. For example, part of the domain could have Dirichlet, part of the domain could have Neumann, and then the remaining part could have a mixed boundary condition. Okay, so this is very much possible in practical applications. For example, you will get mixed boundary conditions in places where you have convection boundary conditions. Okay, and then you will get Neumann boundary conditions where you have some kind of an insulated boundary, some kind of an insulated boundary condition, or if you have some heater that is supplying a constant heat flux. Okay, it could be supplying some constant heat flux or something else. And then, of course, specifying phi equals constant is basically you're saying that it is maintained at a specified temperature or something. Okay, so this is a kind of few examples how boundary conditions could be applied to an elliptic problem. Okay. Again, in elliptic problems, the disturbance, any disturbance that is any disturbance in the interior of the domain propagates instantaneously throughout the domain. Okay, we say instantaneously from a theoretical perspective, but we know that essentially any disturbance created in an elliptic flow domain only actually goes with the speed of sound. Okay, that is the practical speed of sound in that particular material. Okay, so that is the speed at which it basically travels, but theoretically or mathematically we say that it basically travels at the instantaneously or infinite speed of sound as such. Okay, and we note that the solutions to elliptic equations, the solutions are to elliptic equations are smooth even if the boundary conditions are not so. Okay, that means even if you're going to specify boundary conditions as non-smooth, if there are jumps and if there are jumps in values across boundary conditions and so on, even then the solutions inside that we calculate inside the domain are always smooth. Okay, so that's about the elliptic PDEs. Any questions so far? Anybody? Also, I posted your assignment 4, which is due in about 10 days. That is on a solution to ordinary differential equations. Okay, you may take a look at that, and then we can discuss if you want me to go over the assignment problems sometime in one of the lectures. Okay, any questions so far in the lecture?
No, sir.
Okay, fine. So let's go back to this thing. Okay, so let us look at then the parabolic type of PDEs, parabolic partial differential equations. So if so essentially a PDE is called parabolic if b square minus 4ac is equal to 0 in the entire domain. Okay. And parabolic PDEs have one real characteristic, okay, which is equal to b by 2a, right? We have, because b square minus 4 is equal to 0, then you have minus b divided by 2a is the slope of the real characteristic, okay? And examples of parabolic PDEs are, these are typically transient problems, transient or unsteady problems with significant diffusion. Okay, so one example could be the unsteady heat conduction equation. Okay, which is given as tau square t by which is given as partial t by partial t equals alpha times tau square t by rho x square. Okay, this is in 1D. Or we can even write this as alpha times tau square t by rho x square plus tau square t by rho y square. Okay, so that's a parabolic PDE. Similarly, diffusion of viscosity. Diffusion of viscosity. Let us say if I take the x momentum equation for a fluid flow, and then by making certain assumptions, we can show that dou u dou t equals nu times dou square u by dou y square. Okay, this is basically diffusion of viscosity across a boundary. Okay, across a boundary layer, or within a boundary layer. Okay, so this is also an example. So for example, if I'm going to calculate what is A, B, C here, we basically see that A equals C equals alpha, B equals 0. So we have B square minus. Okay, so this is in 2 dimensions. Let me take the 1D case, because I have to apply only one at a time, right? Because this is equal to alpha. Okay, let me take the 1D case. And if I take x and t, right? If I'm going to take x and t as my variables, I have I'm not really considering the second one, because there are 3 variables here. You have x, y, and t. So if I were to deal with only x and t in these coordinates, what I have is that I'm looking for terms which are dou square t by dou x square, dou square t by dou x dou t, and then dou square t by dou t square. You realize that these 2 terms are not there. Only term that we have is here is a equal to alpha, right? Other 2 are there, not there. So as a result, b square minus 4ac will come out to be 0, right? Because both b and c are 0. Okay, similarly, we can show that if it is y and t, it is also going to be a parabolic problem. Okay, similarly here also it is a parabolic problem because the discriminant is equal to 0. Okay, so these problems have one real characteristic, and to solve this problem, we need to specify typically one initial condition, right, and then 2 boundary conditions. Okay, so depending on essentially 2 boundary conditions for each spatial coordinate. Okay, fine. So with that, we'll be able to solve parabolic PDEs. Okay, and the final thing is the hyperbolic PDEs. Hyperbolic PDEs, what we have is if b square minus 4ac is greater than 0 in the entire domain, then we call such a PDE as hyperbolic PDE. And hyperbolic PDEs have two two real characteristics. Have two real characteristics because b square minus 4ac is now greater than 0. You have minus b plus square root b square minus 4ac by 2a, and you have minus b minus square root b square minus 4ac by 2a. Okay, so these two real characteristics will lead to two real characteristics. Okay, in two dimensions. And hyperbolic problems, an example is the second order wave equation, okay, which is given by dou square phi by dou t square equals sum alpha square dou square phi by dou x square. Okay, so what you see here is that let us say a equals your alpha square, b equals 0, c equals 1. Okay, so what you have is b square minus 4ac. Oh, sorry, c will actually become minus 1 because it has come to the right hand side. So this will basically come out to be greater than 0, right? You have c or a, one of them negative, and then you have minus here. So as a result, this is going to be positive. Okay. Okay. So as a result, this is going to be positive. Okay. So that is an example of a hyperbolic problem. In general, you know that essentially supersonic or supersonic flows are examples of hyperbolic problems. Not only supersonic flows, essentially the compressible flow problems. Compressible flows are examples of hyperbolic problems. Okay, they are examples of hyperbolic problems, and then we need to be able to solve these equations. We need basically specify two sets of initial conditions, and then two boundary conditions per spatial coordinate. Okay, that means somebody can specify what is phi of x comma t at equal to 0 as some f of x, and then they can also specify what is the first derivative of phi at x for all time equal to 0, or at initial time t equal to 0 as g of x. So with this initial conditions and the specification of boundary conditions, one will be able to solve these equations. Okay, the hyperbolic problem. So we are not going to look at much of hyperbolic problems in this course. We are going to only look at the elliptic and the parabolic PDEs in this course. Elliptic and parabolic PDEs will be looked at. But nonetheless, hyperbolic problems are kind of good to understand the characteristic lines and so on of things. Okay, so essentially there exists something that is known as method of characteristics. Which is a classical way to solve hyperbolic PDEs using characteristic lines. So remember, we have written down these expressions for characteristic lines by when you have found the determinant of the numerator and set it to 0 and so on. So this basically, what this does is it is basically going to reduce the PDE to an ordinary differential equation along the characteristic lines. Okay, and using this we will be able to solve the ODEs to obtain an answer. Okay, so that is the original classical method of characteristics. We are not going to look at that in this course, but that is how the characteristics and the method of characteristics have originated, and that is how the classification of these equations have kind of evolved. Okay, now we said again these characteristic lines actually stitch together several different solutions of the PDE, right? Because the PDE can have different types of solutions, and the characteristics lines are the ones which are stitching them together. Now this is very visible if you look at hyperbolic, or if you look at compressible flows, which I'm going to kind of explain in a little while. So let us look at an example to understand all the three regimes of the flow, or essentially to look at elliptic, parabolic, and hyperbolic PDEs. Let us look at this two-dimensional inviscid, incompressible, or inviscid potential equation. Okay, inviscid two-dimensional incompressible potential equation. Okay, which is given by 1 minus m square phi xx plus phi yy equal to 0. So when I use subscripts here, phi xx means that we are writing dou square phi by dou x square. Similarly, phi sub yy is dou square phi by dou y square. Okay, square phi by dou y square. Okay, so that's what I mean. Now, let us say this is the equation. Okay, then what is the type of this equation? What is the type of this equation is what we want to know. So to know the type, I have to apply, because this is the second order equation, I can apply the b square minus 4ac that we have just learned, in which case a equals 1 minus m square, b equals 0, c equals 1, because b equals 0 because there is no mixed derivative, there is no pxy terms, right? So c equals 1. That means what would be my discriminant? B square minus 4ac is equal to minus 4 times 1 minus m square, or equal to 4 times m square minus 1. Now, is this greater than 0, less than 0, or equal to 0? Well, that depends on if I tell you what is the value of m. So depending on the value of m, this equation can behave as either as elliptic or parabolic or hyperbolic, right? That is how it came out to be. And now m is basically the Mach number, which is the ratio of fluid velocity to the speed of sound in the same medium. Let us say if I'm going to denote the fluid velocity with u, this is the local fluid velocity, and a is the speed of sound in the medium. Okay, then m is the Mach number. Okay, so let us say if you have m less than 1, okay, m less than 1, that means u is less than a. That means the disturbances that are created are going to propagate much lesser speed than the speed of sound. That means the speed of sound will travel faster, and the disturbances are the fluid is actually moving slowly than the speed at which disturbances are kind of moving. Okay, so u is less than a. If this is the case, m is less than 1, then this is going to be, because m square minus 1, this is going to be negative, right? That means for m less than 1, b square minus 4ac is less than 0. So the equation is of elliptic type, right? M less than 1 actually means the flow is subsonic flow, right? Okay, so that means if I consider, let us say, let us consider a pulse, okay, that has been released, okay, okay. Let us consider a pulse that has been released at a time of some 3 seconds. Okay, let us say some 3 seconds ago, a disturbance was created. Okay, so this was released at t equals minus 3 seconds. Okay, that means it was released. It was created at this point at t equals minus 3 seconds, and it has traveled. Let us say in 1 second somewhere here, in 2 seconds somewhere here, in the 3rd second it has traveled here. Okay, so that is what this means. Okay, so it has. So I'm drawing these arrows here to point out. Oh, not this one. Okay, so I'm drawing the. I'll put some green color here. Okay. So, okay, so it has traveled up till here in 1 second, in 2 seconds, and in 3 seconds. Okay, now we are at t equal to 0, and this disturbance was created some 3 seconds prior to t equal to 0. It has traveled here, but then the source which has created this is now traveling slowly. That means u is traveling slowly, that because u is less than a. And so let us say in this other direction I marked exactly the same equal points. Okay, these are all equidistant again. Okay, so okay, you come here, then at t equal, so, and then the source which has generated this has traveled some distance. Okay, but the speed of sound has traveled up till here, but the source has only traveled here. Okay, and then at t equals minus 2 seconds, it's going to create another disturbance, and that disturbance is going to be okay, it's going to be something like that. Okay, it's going to be something like this. Okay, so that has propagated at t equals minus 2 seconds. So this is now at t equals t equals minus 2 seconds. Okay, and then after t equals minus 1 second, it created another disturbance. Let us say again the source that is traveling, but it is traveling at a speed that is slower than the speed of sound. But the sound has now in 2 seconds it has traveled here. 0 seconds it has traveled here. But then the source has traveled even lesser, and it's going to and the whatever it has emitted at t equals minus 1 second is going to be again is going to be somewhere here. Okay, somewhere here. Okay, so essentially what happens is that in this case your source is traveling slowly compared to the pressure disturbance waves. Okay, this is basically your pressure disturbance, which, or pressure pulse, which we are able to hear, right, as sound. Okay, so source has traveled here, and then this is basically an example where m less than 1. This is a behavior of elliptic type of PDE. Okay, where the disturbance that is created at one instance is kind of travels in all directions almost instantaneously or with speed of sound. Now let us consider a case where m equals 1. So this is the case of elliptic with m less than 1. Let us consider a case where m equals 1. So this is basically sonic flow condition. Sonic condition. So what will happen with m equals 1? M equals 1. Essentially, this is going to be m square, 1 square minus 1 equal to 0. So we essentially end up b square minus 4ac equal to 0. That means we have essentially a parabolic PDE. Okay. That means the source is going to exactly lay, is going to be exactly moving exactly with the speed of sound. So again, this was at, let us say, at 3 equals minus 3 seconds. So this is minus 2, minus 3, minus 2, minus 1. This is 0. So 0, minus 1, minus 2, minus 3. Now, when the at minus 2 seconds, this circle would have been here, right? It would have been a circle like that, right? With a circle like this, and at minus 1, this would have been a circle like this, and so on. But then the source has now the source. For example, you can think of this like an airplane. Airplane is moving in the air, and it is creating disturbances, right? The pressure disturbances. Now, let us say if it has come, u is equal to a. That means it has exactly come to this position, right? And at this position, it's going to again make another wave, and that wave is going to be looking like it's going to exactly travel to t equal to 0. Okay, so this is not the right way. No. Okay, I'm going to just draw it without this help of this one. So that's going to be t equals minus 2. Okay, similarly, when it is at t equals minus 1, it's going to draw another. Oh, this one should have actually passed through this one. Okay, should have passed through this one. Okay, that means what you end up with is you end up with limiting circles, which are all ending up on this line. Okay, and that's your characteristic line. And then what you see is that at t equals, this was emitted at minus 3 seconds, minus 2 seconds, minus 1 second, and this object is now here. The airplane is here, and what you see is that there is no disturbance that is traveling upstream, right? This region is the quiet region, right? Because the pressure pulse hasn't traveled, and this is the uh, zone of action, as they call it, because this is where the pressure pulse is being traveling, and then here this is called the zone of silence. Okay, and this is the characteristic line, which is basically the sonic wave that it is there. You can think of this as a small airplane or something. Okay, so this is basically a small airplane that is traveling. Um, Okay, now this kind of thing is a parabolic PDE. Now, let us say if you consider m greater than 1, that means you're looking at a supersonic flow. You are looking at let's say, an airplane, a fighter airplane, or any other airplane that is traveling at supersonic flows, that is more than the speed of sound. That means u is traveling more than the speed of sound, in which case what happens is you have this pressure pulse that is emitted at t equals -3 seconds, but it would at -2, -10, but the source, the pressure pulse would have reached here in 1 second. But the source which is emitting this thing, for example, it could be an airplane, has reached here. Okay, so as a result, when it releases a pulse here, the pressure pulse, it would have traveled more than this thing, right? So essentially, you end up with a circle that comes like that. Now, at -1 second, it has come here, but then the source has now is going faster than this thing. So again, it would release another source, and that would be here, and so on. Essentially, what this means is that you end up with something like that, which is called a Mach lines, or in 3D, it is called Mach cones, okay, which are basically your characteristic lines. Okay, these are your characteristic lines. And what you see is that there is a zone of action which is included in this cone, and there is a zone of silence which is outside this cone. So as a result, somebody standing here would not feel the airplane, okay, if it is here, if it is, even if it has crossed him, he would not be able to realize it unless this, unless when it is traveling, unless this basically, he enters this Mach cone, okay, until this disturbance touches him, he won't be able to realize. So that is the reason why most of the times when you see supersonic aircraft flying, by the time you hear the sound, the flight must have already crossed you and went. Whereas that is not the case for all the subsonic airplanes that you see, where they are traveling much slowly compared to the pressure disturbance that they are creating. So as a result, you can feel it while it is coming to you. You can feel the sound before, and it would slowly come and cross you and go. Okay, so this is what happens in this case. So again, as you can see, there are these Mach cones or Mach lines are the characteristic lines, which are actually stitching the solution together, right? Because the flow has a different regime outside and a different regime inside, right? Because of these Mach cones. Okay, so as a result, this is stitching the flow together using the characteristic lines. Okay, so that is an example of a hyperbolic kind of PDE. Okay, and the discontinuities that we have talked about can be thought of as the shock wave discontinuities, manifest as the discontinuities of the hyperbolic flow problems that we are trying to learn. Okay, so these are usually encountered in the solution of compressible flow equations. Okay, so we are not going to go too much into detail, but then this single equation, 1 minus m square times Vxx plus Vyy, nicely encapsulates all the three flow regimes and all the three types of the second order PDE that we can get. Okay, so I'm going to stop here. Now we have to go into solving, or how do we solve elliptic and parabolic equations. So how do we solve them using different methods is what we're going to see in the rest of the course. Okay, so that is what we will learn tomorrow. Fine. All right, I'm going to stop here, and if you have any questions, you can ask me. Any questions, anybody?
Sir, how you did the exam, sir?
Oh yeah, I'm still yet to grade. Probably just give me 2-3 days. By 3-4 days, I'll be able to finish grading. Okay.
Okay,
Um,
sir.
yeah. I just graded I was grading the thermodynamics course that I was teaching on campus. I didn't get a chance to look at this, but I had a quick look. I think most of you have solved everything. So
Right, sir.
I don't know. You may all be getting very high scores,
Right, sir.
um, which means the final exam can be tougher.
Sir, that is why we are asking, sir.
Yeah.
Same way,
You
right?
know.
It will be better, sir.
Right. I think the midterm should be easy enough so that you are all interested and continue to study for the final exam. Yeah.
Right, sir. Right, sir.
It'll
Okay.
be great if the final exam is also of the same pace. Sir.
Sorry.
It will be great if the final exam is also of the similar.
Yeah. It will not be similar. It will be definitely one step higher than this thing because now you have learned all these things, so it should be higher. Yeah. It will be good. I think anyway, final exam you'll get 3 hours, so you can think, answer, all those things.
Right, sir. Right, sir.
Yeah.
Okay.
Sir, one question I want to ask you.
Yeah.
Can I ask, sir?
Yeah. Please go ahead.
So basically, sir, while doing the TELUS series expansion, sir, so how do we decide that we have to expand up to like order 3 or order 4, or maybe we have to go something else? Like for example, the tripartite method that we have, like you have taught us actually.
Which one?
While
Sorry.
solving the trapezoidal method, sir.
Correct. Yeah.
So basically, in that you have expanded till third order. And we
Correct.
came to know that okay, this is second order, third order accurate. So
Locally. Yeah.
why can't we go up to 5 or 6 or 7 or maybe 8? Or what is stopping us to just like realize that okay,
Oh,
expanding up to third order will be okay for us, or like.
no, we should.
I'm sorry, I could not get that.
I mean, ideally, we should go for higher order terms also. We should not stop at there. But because we already know. I mean, at least I already know that it is going to be third order. I didn't go more than that. But if we are coming up with a new scheme, then we should go for even higher order terms. Yeah. So we will not know a priori.
What I mean to say, the concept behind that is, suppose you give us a new scheme for timing. I'm just like telling us, sir. And
Yeah.
what is the key thing that we have to look at, that we should expand up to certain orders? Like, what is the guiding principle for that, sir? I'm sorry, I could not get
No.
that.
No. Okay. I think I got the question. See, for example, I think you can see the question in reverse way. For example, to get a second, we looked at this thing. When you want, what is the maximum possible order of accuracy you can get with 3 points, right? If it is a central scheme, then we said, okay, it is only second order accurate, right? That means if I'm going to ask you derive a fourth order accurate central difference scheme, then already know that you don't have to go more than you will make use of some 4 points or something,
Yeah.
right? And then you know that you are already looking at fourth order accuracy, and then the dou square phi by dou x square term will have h square, so you have to go at least up to
So
6 derivative or something.
that is well understood, sir. That you have
Yeah.
like very clearly told us. But the
Yeah.
point is that, sir, suppose in case I'm not asking this question as an exam centric thing, in generic way, sir. Suppose if I'm a engineer and I decided to like for example, like Crank-Nicholson method is like globally h square order accurate, and locally it is h second order accurate, and globally it's only h. But suppose if I try to expand it to suppose fifth order term, so probably I get is globally fifth order accurate, fourth order accurate, and locally third order accurate. So, like what I mean to say, sir, when I'm not having that idea, then how to decide that like order of accuracy? That I was a bit confused. I could not get the link behind that actually. So
No, I didn't get the question. So what you're saying is, are you asking me how do I come up with new schemes?
no, sir. Basically,
No,
you are
not
having the
new
idea
scheme.
that okay, Crank-Nicholson is like globally it is order h square order h accurate, and locally it's like h square is accurate, right, sir? Suppose
No, I think h cube and h square, something like that. Yeah.
right,
Okay.
sir. Suppose if I don't have an idea about that, so I don't have any prior idea that okay, like what is like accuracy of the scheme in that way.
Yeah.
So till how how long I have to expand it in that way? Suppose
No, I think
I'm
then, correct. In that case, you would expand, let us say, up to third order, fourth order, and you stop there, and then you derive the equations. If you are thinking that essentially it is still, if you don't have enough coefficients, enough equations for all the unknown coefficients you have, then you know that you have to go for more, right?
okay.
Yeah, I mean, essentially you want to get enough number of equations for the as many number of unknowns you have. If you are not going to have that, then you have to keep expanding to more and more terms.
Okay, sir. Noted.
Right. And so essentially it is going to be like a trial and error. You try with, you stop somewhere with four terms or something, and then you see if you are still, if you feel that this is not enough, then you have to go for more terms. You have to kind of do a second time.
Okay, sir.
Yeah.
Thank you.
Thank you. Maybe you can come back if you have more questions on this later. Okay.
Yeah, sure, sir.
Yeah. Other questions?
Just a general question, sir, but means okay, it's maybe like kind of expansion of what Roshan has said. So like on the partial derivatives, like okay, like heat conduction, we have that equation is there, like dou square u by dou x square plus I think dou square y by dou x square. Similarly, like okay, if we see something, if we if we see something like some environment or something like this is heat conduction is one case. Similarly, for any other case, maybe there. After like just seeing that scenario, like will be able to means what you call like means through our experience, we'll be able to know that like okay, what are the terms will be involved in that. I understand that like maybe once we know the equation, we'll be able to know the initial conditions and boundary conditions and all those things. But I'm saying like at the when we see the environment or something, after seeing that, we will be like able to, through our experience or through some way, like we'll be able to come up with that, like these are the terms will be involved. So like we'll be like recurring based on this, like approximately like this many initial conditions and this many boundary conditions will be recorded for this.
Yeah. So I think, so what you're saying is that, so when you say environment, essentially you're looking at some kind of a domain where there is some physics happening, that's what you refer to. So you need to come up with what is the governing equation for the problem. That is the first thing. Let us say you're looking at some new, a new physics somewhere that is happening. Then you need to first come up with, through certain assumptions, you need to come up with the governing equation. Now, the governing equation is actually going to dictate you what kind of initial conditions and boundary conditions that you would need. Okay, because initial conditions are related to the time derivatives and the boundary conditions are related to the spatial derivatives. So only from there you'll be able to kind of tell. So that means if you are looking at a new problem, we need to first come up with what is the equation that is governing the evolution of this particular problem. That needs to be carried out. Right?
Yes, sir. Yeah.
Only then we will be able to tell what kind of boundary conditions, initial conditions you would need.
Okay, on the determining the governing equations, like can we like after visualizing or like seeing the domain, can we like determine that this many derivatives will be there approximately?
Yeah, so I think that's a little bit complicated problem. See, I think this is not easy because you need to first categorize the problem into what kind of problem is it. For example, let us say if there is diffusion, then you would know that there will be some diffusion term, something like this, something like dou square u by dou x square. And if you know that there is diffusion going to be in multiple dimensions, then you know that there will be dou square by dou y square term and so on. So you need to first categorize the problem into what kind of a what kind of a transport equation it is. If it is going to be of the transport equation type, like what I mean is that is there some convection, is there some fluid being carried out, is there some diffusion? For example, you open a some dye or some scent bottle or something like that which has some diffusion coefficient. Similar to that, is the species being diffusing into the domain? That is another thing. So you need to first come up with I think the best way is to compare with existing set of equations that we know from continuum mechanics or continuum fluid mechanics, right? You have convection diffusion, you have Navier-Stokes equation, you have species transport equation, you have energy equation. or you have, equations in solid mechanics. First, we have to draw some kind of a similarity or analogy to existing set of equations. Only then we'll be able to compare and say, okay, this is like this equation with certain terms taken to be zero or certain new terms being added, something like that. Only then you can model, a new phenomena that you are observing in relation to the equations that you have already learned or already there in the literature.
Okay, sure.
Yeah,
Is there any
but
problem like that we can see, sir? Like, or like in the like whatever like we have learned so far, can we involve like some kind of a two equations, or I don't know, like it will be possible or not, or you can guide us actually how we can do that? Considering
what kind
like
of equations? Sorry, what kind of
no,
equations?
we have learned multiple equations like maybe heat conduction and all those things.
Correct.
Can we like maybe like involve like okay some domain involving two cases, two scenarios, and whether I don't know like whether it can be solvable through hand calculation, but I'm sure like it will be it can be like the FDM softwares can do that, or like will it be like or some example or some reference if you come across like in the internet applying two cases, how they have resolved that complete scenario, and including the matrix determinant means matrix we know like LU decomposition, all those things we know, but from this initial boundary conditions till the time of discretization, if something they have resolved or like solved it, and if you come across and if you can share us, that will be helpful, sir.
Yeah. I think we will anyway look at this Poisson equation solution, in the 2D domain, that we will see. I think what you're asking is, you want to apply it to some physics problem, something like heat conduction or diffusion or something like that, or even convection diffusion.
Yes.
How the equation is being integrated from some initial condition to some final condition.
Yes,
till
correct.
steady state or something like that. Yeah. We will look at the Poisson equation anyway. That's not a problem. I think you will at least do some, maybe a tutorial, or I don't know whether we may not have time for doing a programming assignment. We'll see. Even if there is some 1 week, I'll try to put in, some small assignment, so that the last week you can do work on that. Yeah. If there is something like that, I'll let you know. I think we will also do that, in the solution of Poisson equation. In fact, if you look at all the CFD problems or all the structural mechanics problems, they are all doing that, using either software or using in-house codes or open source codes. They are solving a particular domain, which is basically, represented as a mesh, and then applying proper boundary conditions, initial conditions, that is being solved till till some final time. So that is kind of a regular thing in CFD or any other computational mechanics problems. Yeah, we'll discuss that mostly.
Sure, sir. Sure.
I will also let you know if I come across something.
Sure. Thank you, sir. Thank you.
Sure. Yeah. Anything else? Anybody? Okay. If not, we'll meet tomorrow at 4 o'clock. Okay. Thank you, guys. See you tomorrow.
Thank you, sir.